Okay, today's talk, I was offered from Francesco about the random number talk, and he wanted to do, when I was talking about the Erlang Factory 2012 in Bay Area topic, I was trying to submit a random number talk again, the second time, but Francesco suggested me to save that topic in Europe. So this will be the first random number talk in Europe about Erlang. So the executive summary is simple. It's like a random number is like a cryptography. So if it's really difficult to do properly, and lots of failure or failed random numbers are existing everywhere by hasty invention. So don't try to invent yours. If you want to sleep in this presentation, just leave this in your mind, please. And this is an old Dilbert's definition of randomness, and it's written that it says that this monster is always returning 9999999 or whatever 9. And it says, are you sure that's random? Dilbert is asking. And he said, that's the problem with randomness. You can never be sure. This is true, and check out the date. It's 2001, very long time ago. And the Debian's security hole was discovered 4 or 5 years ago. And this kind of topic is repeatedly happening in the history. So if you are dealing with random numbers, you got to be really careful. It's as vulnerable as cryptography, and as vulnerable as every other software. So you have to be very careful. So let's talk about the basic topic. What does randomness mean? On Wikipedia, it says it means lack of pattern or predictability on events. And it says no order, no coherence in the sequence, no intelligible pattern or combination. So it's about total noise. And statistically, random processes still follow a probabilistic distribution. Like all number will be a same probability. That is what is called uniform distribution. And in the natural events, there's another distribution called Gaussian distribution. I will talk it about later. And so, what's the pseudo-randomness? Pseudo means if you want to compute something, compute a random number, you can't really do that, because on computers everything is deterministic. So there's no real randomness for the algorithm. There's no random algorithm. So there's a lot of questions that stack over for how can I compute random numbers? The correct answer is you can't. But in the pseudo-randomness means pseudo-randomness stands for a predictive sequence generator with a fairly long period, like the power 2 power of 199.37 or even much longer. This is a very long distance number. And this kind of very long predictive sequence generator can be used as a pseudo-random number generator so long as the beginning point is not known. You cannot estimate where it begins and where it ends. Then that can be used as a pseudo-number generator. And each random pseudo-random number PRNG needs C4 to determine the starting point. And it's also called the initialization vector. And it's actually a function. First you give a value, and a value called fx, and then there will be fx plus 1, fx plus 2, plus 3, or 2 plus 4. It's a function of a continuous integer. It's converting into something like random number. So then what is real randomness? The real randomness will not be coming from the inside the computer or deterministic world. It will be coming from outside, from the more like physical events, which is very unlikely to be predictable to the consumer or the randomness itself. I mean that it should be coming out of the world of the computer or computer network. So, and if you really think about the true random environment, you can't really avoid the interference of the exterior environment. For example, if you use some kind of semiconductor, the level of light or level of external electromagnetic noise, anything else can be affected, can affect the output of the random number or random signal. So if you really have to be sure, you have to think about all the external possibility of external interference. But if you about the measurement of randomness, at least you can statistically measure all the whether a physical random number generator or random signal generator is truly random or not. Or you can change the signal if it's biased into somewhere a little bit plus or minus or whatever level. You can calibrate into something more like a more statistically sound distribution. So let me talk about the notion called entropy. Entropy is a unit of randomness. It's physically a totally different definition, but in the world of information solely, it's a unit of randomness. And this is a definition which I quoted here from a book called Cryptography Engineering. It's a very well-written book, and I recommend you read it all if you really want to tackle into cryptography and engineering. It's available also in ebook. And let me assume that if 32-bit word a complete random number exists, it has 32 bits entropy. This is very straightforward. But if you try to make this kind of thing, this thing won't be happening so easily, because the real random number generation environment using a physical device has a bias or has a skew or some kind of non-uniformity presented. And there's another example. If the 32-bit word takes only 4 different values, like maybe first 2 bits are only changing randomly and the rest is the same, and that means that each value has a 25% chance of occurring in the word. This only reduces, even if the length of the word is 32-bit, it's going to be a 2 bits, only has 2 bits of entropy. So the entropy should be measured by the real change of values, and not by the information given literally. And talking about the Dilbert's case, it's absolutely 0. Same number all the time, same number all the time, same number all the time. It's 0. 0 bit of entropy, and it means nothing from the point of view of randomness. And let me talk about the source of real high entropy sources. There's a thing called thermal noise. Thermal noise is something you cannot get rid of anyway. If you put a resistor or anything, and you measure the voltage coming out of that, there'll be a very slight amount of noise. It's also called a Boltzmann noise. It depends on temperature, how the level is defined. It's a physical phenomenon, and there's another let's say, so event called avalanche noise, and it's a kind of semiconductor event, and I'll talk about it later. And there's another one called optical noise, and there's a device called lava can, which uses, there's a device called a very fluctuating lamp called lava lamp. And you put the lava lamp into a very dark can, and you put the CCD means a video sensor over that, and you saturate it so that the noise will be coming out to the maximum. Then, to generate something physically random. And there's another source of noise, radio noise, atmospheric noise, or what is this? Maybe in British English it's called static. And there's a site called Randomness, which is specialized on generating somewhat commercial, somewhat volunteer-based service of the true random number available throughout the internet. I suggest you to visit random.org. You can learn a lot of things from that site. And there is actually a machine rolling the dice automatically from up and down, up and down, up and down, and taking the photo of these dice, maybe a 5 or 6, each have 6, say, like 6, 5, 5, 3, 1, or 1, 3, 3, 4, 5. And that generates the true random number. I don't know how can you evaluate the actual physical bias, mechanical bias, or whatever, but this is a keyword called dice-o-matic, and I link it to a YouTube site of the photograph of the dice-o-matic. And I've heard that it generates 1 million sequences per day. I don't know how it is useful, but but it's much better than zero entropy. It really has maybe 6 to the power of 5. I don't know, maybe less than 40 bits, less than maybe 32 bits of entropy for each time or something. And I introduced those things, and those things have one thing in common. These are very expensive. Expensive means that one sample does not give you a lot of entropy, and very low entropy bit rate. You can only get 1 kilobit per second, or even if you try 10 megabits per second, it's very hard to obtain. You have to have a special hardware. And I've heard that there's a Japanese semiconductor company trying to use a quantum quantum physics on generating a random number signal. But even that will not give you 1 gigabit per second or something. So those things are not the substitute for pseudo-random numbers. Pseudo-random numbers are easy to generate. It's just a computation. If you make it correctly, you can make it parallelized or use a multi-core generation. But these physical random number generators are practically for seeding purpose only. And the seeding means that giving the seed to the PRNZs later, so that the PRNZ could be more random. And one other thing I have to state is that these things do not necessarily statistically uniform or Gaussian, because these are physically totally randomized. The mean value will not be the center of the given all values. And they'll be going to this way or that way, or this way or that way. You have to calibrate. Okay. So this is the avalanche dial noise generator example. I presented on the 2011 Erlang Factory Conference in San Francisco. And this is the part of the diode. You put positive bias from here to this side, and see this direction is actually on the backward. But when you apply enough voltage here, this causes a breakdown. Breakdown occurs quite frequently, maybe at the rate of 1 megahertz or even more. But it's just breaking down randomly. So and the current will be not so large. So I put the another transistor here to amplify the current and make it this a sort of switch. And I put two circuits here so that the this could be used as a differential circuit to reduce the environmental bias between this chip and this chip. So I'm not going to go deeper into the electronics here. This is talk about Erlang. This is not talk about electronics, but I made this stuff in 2009, and this is Arduino. This is actually Ethernet seal, and this is my seal. And this gives about somewhere around 10 kilobits per second randomness. You cannot expect much because it's Arduino. Arduino is not that fast. I mean Arduino, Duemi and Nobel. Recent Arduino using 32-bit core is very fast, but this is actually a 8-bit core, very old one. But anyway, you can make it by yourself, and but the real issue is that whether the output is truly random, truly in a uniform distribution or Gaussian distribution. You have to measure it very carefully. Okay, so there are lots of things tried in the modern operating system to get the entropy from the various events in the computer. For example, there are lots of so-called unexpected events, like hard disk access duration, or mouse keyboard timing. How you move the mouse, or how you tap the keyboard, or Ethernet packet arrival timing. This is intentionally randomized. Remember, the Ethernet has a protocol called CDMA, and the whole packet timing of the Ethernet is supposed to be randomized. And there's another source of source of randomness of wall clock values, which is microsecond. When you turn off the computer, you don't measure when it will be actually 0 UTC or 00 British time or something like that. You don't use that. So that could be a source of random number. But there's one thing common, which is not random. Those events can only happen after, when the system is booted. And at the boot time, there's no entropy, because nothing happens. Nothing happens with no randomness. So you have to be very careful, depending on the operating system's own random entropy source gathering. And there's a website. There's a website and paper about investigating whole stuff. I put it in a very small letter, but you can ask Andra to get the PDF, and you will be seeing this. And there's already lots of vulnerabilities have been discovered, even on the /dev/random on the Linux. So if you really want to be sure that your machine is okay to deal with the physical random number, you have to boot up 5 minutes or even 10 minutes before it's being used, so that a little bit of source of randomness or entropy is gathered. And I write it in a general form. The solutions to solve this problem is to use an extra entropy generator, like I presented before, or wait for enough time to gather entropy and fill it into the pool. Okay, so let's talk about PRNZs. I repeatedly talk about output distribution. The one of the simplest one is the uniform distribution. If you roll the dice, if every 1, 2, 3, 4, 5, 6 are coming in the same probability of the 1/6, that's a uniform distribution. And there's another event called Gaussian or normal distribution. This is actually representing the sum of those independently occurred uniform number distribution events. And this is pretty common in natural, what do you say? Lots of natural events. And these two are very common, and almost all the other distributions are calculated from these things artificially with the using the converting functions. And about the PRNZ, pseudo RNZ, I was talking about, it's a very long sequence generator, so that the human being could be considering it as a random sequence. So the generation period length should be very long, especially when sharing the same algorithm between the multiple processes. If you share the algorithm on the same algorithm with the 10 core, the 1 core can be given 1/10 of the period. So if it's going to be a 10,000 core, 1/10,000. If it's going to 1 million, 1 million. So actually, this is not a big problem in very long period lengths of random generator, but you have to make it keep in mind, so that to avoid overlapping all the sequence. I mean, you don't want to see the same sequence twice when you deal with independent random generator. So you have to mathematically guarantee that. And this is Gaussian normal distribution. This is what happens when a lot of people taking an exam, and the score will be something like this. This is the mean value, and this is the standard deviation. And if you go to the 6 sigma, I mean the 3 sigma, and the whole stuff will be in this. It's called sigma and 6 sigma. 6 sigma means plus minus 3 sigmas. And the 99.9% will be in this value. And okay, let me go to this one. Right. This is a uniform distribution. I actually generated using Erlang. Uniform means this is uniform. And the lines have, these are 20 lines here. So they each this is a bar of the possibility. It means 5%. And I use it when 10,000 events. So the value is about 500 to 498, 486, 474, something like 500. And what is interesting is that if you make sums of the repeating uniformly generated pseudo numbers, it's going to be more closer to the normal distribution like this. And the mean value is about here. And I'm sorry, I don't calculate the standard deviation actually, but it's more like a bell curve. So this is a tip. If you analytically calculate the bell curve, it's not easy. It's a kind of a complex mathematical function. So if you want to get the Gaussian distribution on a random number, just try. I use a 12, or maybe 6 is even okay. The 6 or 12, or you multiple times of uniform random number, and adding them up and divide it by 12 in this time, and then you will get this kind of a uniform Gaussian distribution random number. This is a practical tip.
What's the 12?
12. I actually picked it from one of the web articles that if you use 12, the value of the square variant will be 1. That was I don't know. My rule of thumb is 6, but I use this as 12. If you use it, going to be a larger number. Let me try. Larger number. It will be, for example, like 50. It will be more like this. But the more you add the large random number, it's more closer to the normal distribution. Okay, so let's get back to Keynote. And let me explain about the recent bugs found about random number. Uniformity is very hard to achieve in the real world. There's an application called CryptCat, and it's a buggy PRNZ written in JavaScript. There was a sequence right here, and this is a miscalculation of a rounding number just by 1, just by 1, and they thought these dotted part were random, but if you take 1 million or 10 millions of random number coming here, this grid will affect the whole things and ruins the randomness of this pattern. So after they fix the bug, they changed into this, and this looks like more true random number. So if you're interested in this, I suggest you to read this article. But this kind of programming error is so common, so you gotta be very, very careful. And this is the old example I presented in Allen Factory 2011 in the Bay Area. I was rather astonished about this. And this is the PHP 5 Windows so-called random number. You see this pattern? See this? You see this? This is great. this is I was very, very surprised that this kind of pattern was actually found in PHP 5. And this is an XKCD, and some people say it's only 4, and chosen by the Fairdash role, and granted to be random, at least for once. For once, but this doesn't give any entropy. This has 0 bit entropy. So if you think about the randomness, think about the entropy first. And remember that it's very difficult to do it properly, so don't try it in ventures. If you aren't sure what you're doing, don't try it. So let's talk about Erlang OTP random numbers. Erlang OTP's random module is the algorithm is actually built in 1982, and it hasn't been changed for many, many years. And it's already 31 years old. And this is the old one. And about the crypto module, I'm not going to go deep into the crypto module because it's, after all, OpenSSL API. So if you trust OpenSSL, this is the hardest part because I'm not going too deep into that, but the recent NSA stuff and other things make these old established crypto things sometimes not untrustable. But if you trust OpenSSL, crypto module will be doing everything fine. So for generating passwords and keys, always use the crypto module, please. Because there was a huge bug in SSH module which is discovered by Jeff Kant, a hacker, talented Erlang hacker in Heroku. He discovered a certain pattern on the SSH module keys, which was not initialized by cryptography, secure PRNG, but he was using the random module. He discovered certain pattern could be repeatable and attackable. And I think this is the first ever CVE on the Erlang OTP generated. A very, I should say it's a wall of shame, but it's better be discovered rather than not being discovered. So it's fixed on R414B03. So if you are using R40B02 or pre-version or previous version, don't use it. Update to R40B03 or something. And 2 years ago I measured Erlang's pattern, similar to the PHP's pattern. This is good. At least I don't know whether it's random or non-random. But this is a very intuitive way to find out whether a pattern is random or not. And this is the source code. Only this. And this hasn't been changed at least since R14B02, or even much in the earlier version. Maybe you can track the source code repository on GitHub or the history, but it only uses three numbers, three prime numbers, and seed has three random numbers B1, B2, B3, and they will multiply them and takes a remainder and adding it and truncating it. That's it. This is a very old algorithm. And of course this, I'm not saying all things are bad, but AS1 AS3 is the code name of this algorithm, and this algorithm has been known as some deficiency. For example, the period length is short. That's about 43 bits, and 43 bits is not so long. It's about how many? 10 trillion times. Trillion means 12 digits of the decimal, and it's very easy to count on this event in modern days of computing. And it's all designed, and it's not designed for parallelism. Not designed means you can't choose many internal states, because the number of internal states will never be larger than this number. And seed has only 3 16-bit integers. Only 3 16-bit integers. This is not sufficient for a very large-scale simulation. And this algorithm is not designed for speed either, because you have to use a floating division and floating addition, and all those are very high-cost computing. But one good thing is it's pure Erlang code, and that is very good. So think about this. I think the next generation, or a random module should be improved in a more modern way. For example, larger period length PRNG should be as a standard or an alternative, actually. And there should be a new or modern design things, and there will be a parallelism requirement. Parallelism means using the same algorithm with a massive number of processes or cores or whatever entities or computing entities. You can map into the Erlang process or Unix process or whatever. But the number will be massive. And if you try to guarantee that the sequences used by each process is not overlapping with each other, I mean, it's more difficult. What it says orthogonal. You have to use the mathematically proven algorithm so that given given those parameters can ensure the orthogonality. And there should be a larger state length proceeding, which is virtually the same meaning with a larger period length. And I would say in Erlang, pure Erlang code is always better for the scheduling, but for the speed, NIFS is better, always better, especially for batch computing. And batch computing means doing the whole computing, intensive computing stuff in C, and controlling back into Erlang. And those are required to suggest features of parallelism. Each parallelism has to manage its own state, and the independent or orthogonal sequences from state algorithm should be obtained in a mathematical way. One of the things you can do is that splitting the internal state. If internal state has certain 100 bits, such as 600 bits or 700 bits, you can use the first 10 or 20 bits for the process number, and the rest will be assigned as the individual random sequence. Or you can guarantee that use the polynomials to use the random polynomials. I'm not going to get into details because this is math. And I'm sorry, I'm not so good at math, so I cannot explain what's the orthogonality of mathematical practice of polynomials. But in certain algorithms, at least quite a lot of numbers polynomials can be obtained. So using the different orthogonal polynomials is also important. And there's another method called seed jumping. Seed jumping means hopping millions or trillions of calculation in a very fast, skipping to the over 1 trillion or even more, so that the even using the really same algorithm by jumping giving this jumped seeds on each process, you can guarantee at least 1 billion or something like that sequence will not be shared with each process. So there are two alternatives I implemented. Oops, I implemented. Actually, I made spelling mistake. I made this SFEmpty Erlang and TinyEmpty Erlang. I will explain those keywords called SFEmpty and TinyEmpty. And these are both available at GitHub. And I published a paper, actually 2 papers, on the HTML workshop. And unfortunately, HTML has a paywall. But I also submitted the almost similar version on my own website for free, so you can get it by you can read by yourself. And one thing I have to say about these two algorithms are not secure. Not secure means that not cryptographically strong or whatever. So these are just PRNTs, very long sequence array. And before talking about the SFEmpty or TinyEmpty, I'd like to talk about MT part. MT stands for Mersenne Twister. Mersenne is a name of a very famous mathematician of France, a long time ago. and there's a number sequence called Mersenne number, which stands for powers some number power to -1 is prime, and I think that I don't know the largest Mersenne number, but it's more larger than this. But this is and the Mersenne, the person called Mersenne discovered this pattern, and that's one of his lots of mathematical contribution. Okay, back to Mersenne Twister. One of the good things is that it's BSD licensed. It's not GPL, or even stricter license. It's BSD license, so you can do it whatever you want, so long as you mention the whole author's name in the source code. And Professor Matsumoto and Professor Nishimura, these two people are real mathematicians, and they invented the Mersenne Twister in 1996, and it has a very long period, 193.7. It's almost 20,000 bits of number, of integer, so it's really hard to count. Maybe counting these will not be complete with it, or maybe our civilization will extinct earlier than counting this. And it's mathematically proven that it's uniformly distributed in 623-dimensional cube. The cube is only 3 dimension, and I cannot really imagine what the 623-dimension cube it is, but they say it's uniform. So it's uniform is at least counting 623 secret number that will be in the uniform manners. Anyway, this is a very good PRNG, and it's widely used or implemented on many open source projects, such as R. It's a statistic language, and Python. It's modern and used everywhere. Invented in Google, GitHub also. Or mRuby is a modified version of Ruby. It's an embedded Ruby, and it has Mersenne Twister as one of the default random number generator. And SFEmpty is a modified version of MT, and Professor Saito, who is now actually working on MT and other stuff, and Professor Matsumoto made it together in 2006. And it's optimized for x86 and x86-64 or AMD64, the Intel architecture. And they also made it for PowerPC architecture too. And there's a various period lengths supported from 2 powers 607 to 21691. I don't know whether you are going to use this, but these are they have given test case publicized so that every implementation can check all the genuineness of all the sequences. And there's another stuff called zero access initial state. Zero access initial state means that if you put zeros on all the seed, the 600, maybe 600 or 732-bit words, it's really hard to coming back to put into 1. Zero turns into 1. It takes a lot of time. But on SFEmpty, this recovery timing is getting more shorter. So I should say it's more suitable to be used as a pseudorandom number generator. And SFEmpty Erlang is a very straightforward implementation of SFEmpty in both pure Erlang and with nibs. And I measured it in various period lengths, and I conclude that the MT standard of this length is the fastest one, and which has the least overhead. So I suggest use this. Though in the source code there's already I put in the various period lengths of the SFEmpty. And with NIFs, it's 3 times faster than random module. So if you need a random module, a random number PRNZ with a fast one, from being called from Erlang, you can use this. And one of our friends, Kostis Sagonas, has chosen SFEmpty Erlang as a part of their testing tool, alternative to the random number, a random module. So, let me show you a part of SFEmpty code. It's like this. Maybe you don't understand what it's all about, but SFEmpty is all about recursion of lists. Like if this is list, it choose value here, value here, value here, and value here, and make the exclusive or some manuring of those bits, and try to generate the output. And this this output will be coming after from here. So think about this. It's a kind of sequence. First in, first out, and if the old one's going to drop from the left, and the new one is coming from the right, and it's like a shift register. So it's coming left and right, and left and right goes that. And so let me tell you, it's this is actually source code, and it's a huge amount of sequence. But the original SFEmpty code in C was totally optimized by the static, mutable, which is completely different from the Erlang style code. But I restudied the original paper so that whether the Erlang's advantage of having all the recursion things could be applied. And I did it in a very rather straightforward manners, and I'm sorry, I don't remember the whole stuff because it was 2 years ago. It's really hard to remember, but I put it on my paper. So if you are interested in the detail, please read it on my paper. So let's get back to Keynote. And there was some porting tips of code from C to Erlang. The reference code of SFEmpty was in C, and it was written in static variables in C. Static means everything is mutable, and the mutable thing cannot be handled by Erlang natively. So you have to remove all the static arrays for the internal state table. That's something not so trivial. You have to think about the overlap or other things, or lots of assumptions or other things like that. And I told you as before, SFEmpty itself can be written as a recursion. So if something can be written as a recursion, it will be easier to implement in pure. And there's another thing I found in Erlang version of SFEmpty, that adding elements to the heads and doing the risk reverse made the code 50% faster than using the append operator. But this is a very trivial coding style in Erlang. But on SFEmpty, this was very effective, and I was very surprised, and I was very glad to see that sometimes functional way of thinking could be useful for even this kind of stuff. And about the speed difference between C and Erlang, this is also kind of trivial thing. if you really write a good code in C, it's always faster than Erlang. Remember, Erlang is running on VM, especially for this kind of computing intensive code. And on pure Erlang code, it's 300 times slower than C. On NIF code, it's still 10 times slower than C. So it's the speed up is 30 times speed up. So it's a lot of speed up, but there's some dilemma you have to face. Speed optimization is almost always important. But on Erlang, as long as you're using Erlang VM, you have to have some overhead. So it won't be a real supercomputing code. It's, after all, written in Erlang. So let me talk about TinyEmpty. TinyEmpty is a more dedicated for more smaller memory footprint. Smaller means actually it's 7 32-bit integers. So you can embed TinyEmpty into the microcontroller. And it's also embedded by Professor Saito and Matsumoto in 2011. And the period is very short, to 127. The internal state is about 127 bits, but still it's much longer than the 43 bits. So this is practically quite useful. And the good thing about this is that you can get as more as 2 powers of 56 independent generated polynomials if you compute. And this value is not analytically obtained, but this is empirically obtained by the during the polynomial finding process. And the TinyEmpty Erlang is a much straightforward implementation of TinyEmpty, and there are a lot of code I actually steal from the SFEmpty Erlang code because those are very similar. And let me show you the code. Actually, this is it. This is all. And you can say this is bad, very bad code. You don't have to use. This is record structure called int state32, and there's a 432-bit integer status 0, 1, 2, and 3. This doesn't have to be this kind of symbolic thing. This could be there would be a more optimization, but for Erlang, in Erlang, you cannot assume a word is adjacent to the next address or something like that, unless you are going to handle the whole full 32-bit integer into one big dump, and computing the left shift and right shift in huge big dump would be very slow. So I'd rather implement it in direct implementation or implement porting from C into this code. And on TinyEmpty, this next state function is updating only the internal state, the internal state machine. And the actual random number will be coming out from the function called temper, giving the internal state. So the internal state is not directly representing the random number itself. On SFEmpty, internal state is directly representing the random number itself. On the other hand. If you are interested in this code, you can go to GitHub or read my paper. And this kind of bit shifting or doing AND or exclusive or bit calculation is very suitable for high performance Erlang, because on high performance Erlang, these are going to be all encoded, compiled into machine language. So I obtained 3 times of speed using HighP. And this is HighP is not necessarily well accepted in our community, because in many CPUs HighP does not work well. But for this specific case, HighP works very well. And the wall clock speed, on measuring wall clock speed, this is the speed is same as a random module. But when you use the FPROF profiling this, the calculation takes 2 or 6 times slower than random module. And I regret to say this, but I still cannot track down the actual bottleneck on this. And let me show you the observations on the TinyEmpty Erlang code 2. And there's a pitfall about 32-bit Erlang. On 32-bit Erlang, 32-bit integer ops are all big numbers, because small integer on 32-bit Erlang can only have 20 bits. On 64-bit Erlang, doing the 32-bit calculation on 64-bit Erlang, this will be no problem. But on 32-bit Erlang, this will be a huge problem. The code speed will be very slow, so you have to be careful on using the full word length calculation. And about the overhead calling function and beam memory allocation might have taken a significant portion of the time. I measured it in various different ways, but I still can't get the definite clue about this. But those evaluations suggested that the function calls has a lot of overhead. And one of the interesting things is that SFEmpty Erlang batch execution is still faster than TinyEmpty Erlang batch execution. So there must be there might be some way of improving the algorithm itself. And about the Erlang itself, I'd like to emphasize one thing, which is not only applicable for the random number or any NIF stuff. This is applicable for anything when you try to use NIF. The principle is that a NIF execution blocks the entire Erlang scheduler. So if NIF takes 700 microseconds, the whole schedule stops, and the Erlang VM will not give the time, or give the chunk of time into any other processes. So we should you should find out how long can a CPU spend time in NIF. The rule of thumb is that written in Erlang documentation is it should be less than 1 millisecond, or otherwise the schedule will be crippled. And I personally set the target for SFEmpty or TinyEmpty Erlang in modern CPUs 100 microseconds or less. So so even if you use the NIF version, this won't be blocking so much. But as a bachelor person, I'd like to state that on React, this has been a very, very serious issue on handling database NIFs like E-level DB or other stuff. And one of my colleagues, Scott Fritzy, who is now in Japan, actually, he's no longer in Minnesota, he's in Japan, and he's working with us. And he has openly publicized an MD5 calculation example of using NIFs, and how the scheduler setting will affect the efficiency. So thinking about this stuff, some people demand me that there should be a pure Erlang version on every random number implementation I make, so that those people don't have to think about this if schedule block thing. Okay, and I did a very crazy thing. Used about 2 years ago using a Kyoto University supercomputer, so-called supercomputer. Supercomputer means 500 or 600 nodes of 32 core computers actually, and those are shared. And my budget only allows using 32 cores at the simultaneous time. But the good thing about this is that this cluster is maintained by the technical staff of Kyoto University, and they are working very, very hard for continuous operation using a huge amount of electricity dedicated for this stuff. And I could run 32 days of continuous execution using whole 32 cores. And I calculated 256 mega number of polynomials. And I put them into the GitHub. But the GitHub repository takes 40 or 80 gigabytes. So you shouldn't clone it, or otherwise you're going to kill the GitHub. Don't clone it. Don't clone it. Maybe the GitHub people will get angry about that. But to tell you the truth, for the modern 64-bit computer of maybe 2 gigahertz of CPU clock and AMD 64 or Intel 64-bit IA64, IA64, that's it, architecture, the calculating speed will be 18 to 19 cents per second. So it's not that fast. So I don't recommend you to generate this polynomial real time. Although in many circumstances you can use the real time type of generation. So okay, as the last of my talk, I would like to talk about secure PRNGs. I didn't want to involve deeply in the security, because security is a very, very sensitive topic. Recently, a government institution in the United States says that all existing cryptographic algorithms can be circumvented by their efforts. But I think that is kind of extreme situation. But it's really hard to make the one-way function. One-way function means that you can generate the output from input very easily, but you cannot guess the input from the output without making a very huge amount of computation. And the secure PRNG should be a one-way function. And a PRNG is less secure when the generation period is shorter, because it's more easier predictable. And if easy function exists to get the internal state from the output. Now sometimes this will happen if on the cryptographic algorithm, if there's a certain weak keys, like a length of zeros, lots of zeros, or only a very few bit of ones or something like that. That kind of keys did exist in the DES, data encryption standard, an old algorithm, which is not recommended in the current implementation, but those things surely exist, and no one can guarantee that those things will not exist in the current algorithm. So you gotta be careful about this. And the another issue about the weak security is that if the output sequence is predictable from the past output sequence, that will be very, very bad, very bad. So, so the reason about this, so because of the sole reason about this predictability from the previous sequence, any kind of the simple PRNZ, it should be called insecure. So don't use them. Don't use SFEmpty or TinyEmpty for passwords or anything else. You really need security. And for building more secure PRNZs, reducing predictability is always good. And if you want to generate a little bit more secure sequence from the existing PRNZ algorithm, always try to incorporate necessary external entropy. External means out of the computer system, or out of any system, out of the network, or out of the environment, or whatever. And you should also have cryptographic strengths. Use well-proven algorithm. For example, AES, to encrypting unsecure PRNZ output into secure with the AES will at least obtain the security of the AES, or even less. I cannot say it's even more, but it's even less. But it's not. It's much better than not doing anything. If the AES key is gonna be randomly obtained from the external entropy, that would be much better. And for the other, the rule of thumb is always use crypto strong round bytes. This is rather a new function from I think R15 something. It's available on 60B to guarantee sufficient entropy is consumed. If sufficient entropy is not consumed by this function will draw or will generate an error that the entropy is not available. And let me explain the typical parallel execution of PRNZs. And I've been repeating this many times, and using completely different orthogonal independent sequence like this and this. This and this doesn't cross on the whole point. And the seeding, about seedings, if the seeding space is large, you can just put the PRNZ's output into the other PRNZ seed, and the rest will very less likely to conflict with each other. I don't know. This is not mathematically proven, but this can be tried if you just want to use the different stuff on a different process, and if you don't need the strict orthogonality of the old output. And for the simulations or testing purpose, sometimes the exact output of the exact behavior of the whole system is required. And if you try to do the parallel execution, parallel generation, everything on the parallel, on the ARM process, they all concurrent things means almost always asynchronous. So it won't be like A, B, C, and D. That should be A, D, F, A, psi, F, or something like that. Sequence will change. So the always beware of execution sequence change when predictability is important. And about secure PRNZs, I repeat many times, don't invent yours unless you can hire well-experienced cryptographers. Those people have special sense of mathematics and all those algorithms, which I don't have. I should emphasize to the camera, I'm not a cryptographer. When I read my respecting cryptographer called DJ Bernstein, who is also inventor of QML, I don't know how his brain is thinking. So don't if you are not sure, don't do that. Let the professionals make the algorithm. And ensure the system has enough entropy to guarantee the unpredictability. This is I mentioned it a little while ago. And external hardware is always suggested. And this external does not necessarily mean really external. For example, some Intel recent CPU has its own hardware random number generator. And I don't know if it's crippled by the NSA, but if it's not crippled by the NSA, it would be trustworthy. And let me repeat, don't let the NSA cripple the algorithms. These things should be open source and openly evaluated and openly implemented, and there shouldn't be any backdoors. So to sum it again, this is the XKCD about about the consequence of how security holes are built. But anyway, don't try to invent your algorithm if you are not sure what you're doing. So it takes quite a long time, and thanks for listening. Any questions?
Why don't we have him over a beer?
Yeah.
Yeah. Okay. Thank you so much.